Okay, we have here an interesting integral from the MIT Integration Bee 2025 Quarterfinals Tiebreaker number 2. We have the integral from 0 to 2, floor function of e to the x dx. And I already did a video on this. This is going to be method number 2. And the other video, what we did is I did a u substitution on the e to the x. The reason for that is, well, then it simplifies this and then we can break it up on integer bounds. I like to do that a lot, but there's another way that's probably just as good. I don't really have a preference, but what I want to do instead is just go right away breaking this up in a way that's going to simplify it. And so the way I want to do it, instead of breaking up our integral on integer bounds, I want to find something else convenient. For a starting point for 0, I can actually write 0 as natural log of 1. And then if I create my upper bound as natural log of 2, then we're not separated by an integer anymore, right? Because I don't know what that value is. I think it's been like 0.69, but now we're not separated by just an integer amount. But our input here is separated by an integer. Now this is still going to simplify our floor function because the reason I chose this, let's just look at the upper bound. If we plug that in for x, if we look at e ln 2, well, this property of e in natural log, this basically cancels, and this value is just 2. I guess we could do the same thing for ln1, right? So e ln1, that's going to be just 1. So what this does when we write this part right here, this e to the x, is always going to be between 1 and 2. What the floor function does is it rounds us down to the next greatest integer. So in this case, with these bounds, we're going to get rounded down to just 1. And so we'll just keep going like this. For the next integral, I'll break it up from ln2, starting at this point, to ln3. Same kind of thing's going to happen, right? We're going to be going from 2 to 3 now. If I have e ln3, this is going to be 3. Between 2 and 3, the floor is going to round us down to 2. This pattern's going to keep going this way. Let me do the last one because that one's a little strange. What I wanted to do is I captured this value. E squared is something like 7.3-ish. You can tell like e is less than 3, so it's definitely going to be less than 9, but it's actually less than 8 as well. So for this, the way I can write 2 as ln e squared here. So just knowing this is something like natural log of 7.3. So then what I can do for the lower bound here is write this one in as natural log of 7. But this is going to work the same way this worked over here, where we got back this input on the lower bound. Here, we're going to get rounded down to just 7, because all of our values of this are going to be between 7 and like 7.3. So when we do the rounding, we get this. But this is pretty nice because we've got a pattern that we can summarize. We can turn this whole thing into a summation. I'm going to do this last one separately. So what we'll do is we'll go n from 1 to 6. And in each case, we're going to be just integrating a constant, which is going to be n. In every case, we're integrating n, and then it's going to be, the pattern is natural log of n to natural log of n plus 1. And for the second one, we'll just integrate it. It's just integrating a constant. So when you integrate 7, you get 7x evaluated from ln 7 to ln e squared. Coming back to this one, I think we can just integrate this. So when we do that, we're going to get nx evaluated from ln n to ln n plus 1. I'll kind of work these in parallel. So here, when we plug in, so we already said this is 2, so I think I'm going to put it back that way. I just wanted it to be consistent before. So if we put that back as a 2, what we're going to get here is 2 minus ln 7. Now, if I multiply in the 7 here, we can bring like a 14 out front. Coming back to this part, when I evaluate this, let's see what's going to happen. So we're going to have this. This is all still within the sum over here. We've got n times ln n plus 1 minus natural log of n. And then at the end, we got distributed in this 7 here. I wanted to separate. This is just a constant, so that's why I separated this out. And I still want the ln over here. So this is going to be minus 7 ln 7. But now for this part here, we can deal with this with log properties. Just because we're subtracting, we can turn that into division and also bring the n into the exponent. So what I'm thinking, and this was the exact same in the other video, so I'm going to go a little quicker with it, and I'll provide a link to that other video. So I can write this as natural log n plus 1 to the n over n to the n. just doing the log properties on it. And then let me plug this back into the sum. I'm going to clean up the board and then we can finish this off. Okay, now we brought this first expression over from the previous board. To save this step, what I did is I just expanded all these terms out, just plugging in n starting at 1, plugging in and iterating through it. We get this kind of expression with all these natural logs. One thing I did though, with this natural log with -7 ln 7, I rewrote this just with log properties, bringing this into the exponent, using the minus sign to bring it into the denominator. What we can do is write it this way right here. But now again with log properties, because we're adding up a bunch of natural logs, we can turn that into multiplication and then just multiply together all of these inputs here. So let's see how that's going to look. And the reason for doing that is because now we're going to get all kinds of cancellation, because just looking, we've got the same terms kind of everywhere. So 2 to the 1 over 2 squared, I can cancel that with one of these. Cancel 3 squared with 2 here, and we just left with a 3. Here, this is just going to leave a 4. Same thing. Sorry, that's just still be a 5 there. Cancel one of these. Even here, 7 to the 6 over 7 to the 7, that's going to cancel and just leave a 7. The whole numerator is gone. This is all going to become a 1. This 1, we can leave it, or we can make it. We can just leave it because you'll notice 7 times 6 times 5 all the way to 1. This stuff right here, this is going to be the same thing as 7 factorial. So cleaning this up, what we have is 14 plus natural log 1 over 7 factorial. This can also be written as 14 minus natural log 7 factorial, just bringing that into the numerator. I kind of prefer it this way, but MIT's got it a little different. They expand that out, and so for my final solution, we've got 14 minus natural log 50/40, and that's it. I think if the year was 50/40, I could go along with it, or if this worked out to 2025, I could go along with it, but I kind of like the more compact version, but I'm probably just nitpicking, so that's fine too. Okay, that's it for today. Thanks everyone for watching. Have a good day.